So we kind of want to start off with prefacing this that we did not think a Rust talk would get into a Scala by the Bay kind of conference, but it did. And in no way is this kind of an introduction to Rust or an introduction to some of the actor systems that we built or failed to build. It's much more about kind of the beauty of modern low-level languages and how they can help teams be more efficient, solve problems more in a more performant manner, as well as kind of what it means in practice for companies and teams of developers out there. The other piece that we want to preface this is that Bryan found out he was giving this second part of this talk about 20 minutes ago. So we'll see on the range of disaster to great where we exactly stand. But to start off with, just a little bit about myself and about Bryan as well. So I'm the CEO and co-founder of Datalogue, where we use AI to automate data preparation, and we'll talk a little bit about the things that we do and the challenges that we face. But at the same time, I'm also a health tech master's student at Cornell Tech, where I study mainly weak AI and distributed computing. And also, this is kind of my preferred stack. It doesn't tell you much about me other than I'm kind of jack of all trades, but a master of none. And I just really like to find interesting tools that help me solve problems and interesting problems out there in the wild. Bryan is the CTO and co-founder of Datalogue. He was previously a software engineer at ClassPass. Interestingly, he has an MBA. And his preferred stack kind of falls into the infrastructure as code kind of environment, and he does some magical things for the engineering team at Datalogue. So let's kind of kick this off and talk about how I built an actor system in Rust, kind of, and what the lessons learned there were. And as context for the talk, not sure if any of you guys know who this guy is at the right here, but that's Rajat Manohar, and he's one of the gurus of asynchronous computing. He designs asynchronous chips, and my buddies and I just happened to take one of his classes on distributed computing last semester at Cornell Tech. And Rajat teaches the class by teaching distributed computing using C's OpenMPI library. That's a message passing interface library. You guys might be familiar with the paradigm, but it's kind of the de facto standard for high performance computing, at least in the academic settings. And our goal was to kind of create a cleaner, easier to use, better abstracted, higher performance on average message passing interface than C's library. This thing is like decades old, so it was kind of a big undertaking. And we wanted to do it in Rust because Rust is an awesome modern programming language that's low level, but also has some of the great abstractions that we're used to, pattern matching, zero cost abstractions, and things like that. And we wanted to do so in about 3 months while being full-time students and founders. So ultimately, we were fucking insane. And so we went out and we built Crow, which was an actor system that we implemented in Rust. And then all throughout the semester, we were using that system that we built to solve interesting problems, anything from finding the dividers of a large integer to kind of doing MapReduce and those kinds of typical problems that one would generally face in a distributed computing class. So I want to kind of show you guys a quick little example. For anyone who's familiar with Rust, this is going to look quite dirty. You could have built something that was much cleaner, had better levels of abstractions. Like for example, we have these weird brackety things here where, like for all the Scala folks, this looks super dirty, but we borrow kind of a mutable construct, which is our system, add actors to it. Then we can pull those out of the system and then just send messages and kind of in a similar fashion that you would just in Akka or something like that. We define these actors a little bit higher in the code. But not to dig into details about kind of the Rust implementation, but here's some of the accomplishments. So in this task, we were asked to find the dividers of a very large integer. And what we did throughout the entire semester was pin an intermediate to advanced C developer versus our team. We were complete rookies in Rust, like had never used it before. We had just built this actor system. and we had very, very little bandwidth to accomplish these tasks. And these are some of the performance metrics that we accomplished. And really the lesson learned here is not that we're twice as fast as a C implementation, because a perfect C implementation would have probably beat us, but that we are able to accomplish these tasks on kind of similar resources, solving the same problems and building the similar programs, and do so much more efficiently. And in this graph, this was after like a week's worth of refactoring by the C programmer, and he was still twice as slow as we were. In the first implementation of his program, we were 6 times as fast. So what that kind of speaks to is how modern programming languages and kind of their constructs help us build better programs and deploy those programs more quickly. So we really didn't outperform C in any way. We just showed that really ease of use and modern languages matter. So as you guys are kind of building out your teams and you're thinking about solving really interesting engineering problems and might need some sort of low-level performance, then Rust is a great alternative to C, just because your teams are probably going to get things done much more quickly and in a more performant manner. So kind of that boils down to, like, to drive home the point, I guess, is that great modern languages make programs more efficient and performant, not by just optimizing bits here and there, but really by allowing us to reason more effectively about the programs that we write, by preventing common mistakes. So I'm not sure if you guys have used Rust in the past, but there's some awesome errors that pop up when you do something stupid. Scala's new .12 version is also like moving towards these really useful errors. And they allow you to easily leverage all the computing resources that you have on a machine. I have this beautiful Scala example where it's just like trivial to start leveraging all the cores on a machine. It's almost as trivial in Rust. So now you guys might have remembered what the original title was, how we built an actor system in Rust, but then actually built a company on Akka. And the reason we decided to make the switch was there's a few wish list items that you truly need to build a high quality actor system. And those, when we were implementing our version of an actor system, just didn't really exist. Like zero cost futures, async IO, there was a library out there. It was just tremendously hard to use and very opaque in terms of how it was constructed. And we just needed kind of more mature networking libraries, so that once we truly started to think about not just scaling on a single machine, but then moving to entire clusters, we needed kind of these items to be checked off of the list of things moving forward in Rust, and they just weren't there. So that's when we decided to kind of kill Crow for now. And hopefully, as some of these things start maturing in the Rust ecosystem, we'll be able to move some of our high performance computing needs back to Rust and off the JVM. So I'm going to pass it off to Bryan now. We're going to do an awesome handoff of this mic, this camera mic. So yeah, thanks.
So yeah, as Tim said, I found out pretty recently that I was going to be coming up and doing the second half of this talk. And I guess the idea of telling everyone here why Scala is great when you're all here for a conference on Scala is a bit silly. So hopefully we can just share a little bit of insight into how, as a small kind of scrappy startup, we find that Scala works really well for us. So Tim mentioned before, but we build systems that leverage AI to automate and scale data processing. So data classification, ontology mapping, deduplication, basically all of the messy, dirty parts of data science, we're trying to abstract and automate away. Kind of the scope of things we're dealing with, our first pilot project was processing 30 terabytes of data for our first client. And unlike, I guess, building a system where you're dealing with streaming data and have the same kind of data coming in every day, every time we sit down with a new data source, and we're dealing with this all the time, it's always new and unknown. So we wanted to work with a language that had really good existing tried and true systems for data processing. And so Scala being a much more mature ecosystem than Rust, obviously, we can kind of build on the backs of a lot of mature data processing frameworks, like Spark, for example. And we're also dealing with a lot of crazy weird data formats. So just typical stuff like JSON, CSV, and then customers giving us SQL dumps, dealing with HL7, healthcare data formats. So we kind of have to be ready for everything. And we're also heavily resource constrained. We're a small team. We're dealing with a lot of data. We've had some help from AWS as far as our infrastructure costs. But we wanted to be able to take advantage of a language that was built for distributed and concurrent frameworks. So I guess I already talked about scalability, reasonability and correctness. So for us, when we're kind of building a startup and hiring people quickly and trying to sort of build these systems very fast, obviously some code review practices go out the window and you're trying to get things done. So what's nice is when you build something in Scala, I think more so than a lot of other languages that are out there right now, much more so than Python, somebody else sitting down to the code can read through it and understand it much more. And I like that Scala encourages but doesn't enforce the use of pure functions. Again, when somebody kind of writes something that works in a functional manner, you don't have to think too much about that. You can kind of just walk through it and understand what the steps are doing. And streamability. We've gotten a lot of benefit out of Akka streams for doing some large data processing. Again, being resource constrained, we don't want to host and build out all of our own infrastructure. We want to leverage existing infrastructures of our clients. And so that means as much as possible, pulling data in, doing our operations, and giving it back. And so again, Akka streams combined with Akka HTTP interfaces has been really, really helpful. So the transition from Rust to Scala actually kind of began before I came on board. And I like to joke that Tim chose Scala once, but I've had to choose it a few times. So as somebody that's been coding in Scala for 5 or 6 months, I've had some fits and starts. I wasn't always completely happy with everything. But I think what really solidified it for us is just that the end result of Scala code by us and by people that we have working around the country, because we're a distributed team at the moment, the end result is just really solid and resilient. So better scalable, faster, more productive. Again, the community and quality of open source code for Scala is just astounding. We were on Google Cloud Platform for the summer and trying to figure out how we're going to interact with all of their services. And it just so happened that Spotify had just transitioned to Google Cloud and had built all this really amazing Scala code. So you're able to kind of like build on that and leverage a lot of existing quality code. And yeah, like I said before, everything that we put into production has been rock solid. So I guess
that's it for us. We can maybe do a Q&A.
Yeah, no, we have about 7 minutes for
Cool.
questions and answers. If there are questions, guys, you should repeat the question for the camera.
Cool.
Sure. Yeah, any questions?
I have a question. I haven't used Rust much. What kind of Rust features would you like to see in Scala?
That's a good question. I think it's more the other way around, where there's a lot of Scala features I would like to see in Rust. So I guess I have to double mic this, right? So really, in terms of inheritance, Rust isn't all that great. So it's very hard to re-leverage a lot of the code that you're writing currently. So currently, I would say the best uses for Rust are when you have a very kind of small in scope problem that just needs to squeeze every ounce of performance from your machine. So I'd like to see it grow a little bit more in terms of how you do inheritance between the different structs, how you start implementing better traits across different kind of code modules that you're building out in Rust, just so that the code can be a little bit more reusable and dry. But like, in terms of just things that we'd like to see, is just the performance is outstanding in Rust. So I think what could be pretty cool is to see a better kind of Java interface when you're writing code, Rust code, so that you can pull it into a Java library and kind of squeeze the ounces of performance that you might need for a scope problem. And right now, the interfaces for Java are, I think, kind of in the works, but not very robust. No, there's great Python ones right now. Any other kind of interesting questions? We're also happy to geek out about a whole bunch of other things as well. We got two. We'll go here and then go back to the left. Yeah.
I wanted to ask you, so you use actors mostly for concurrency, or like how is the process? You're talking about performance? Java itself is not that much performance.
Yeah, so it's much more about actors for layers of processing than it is for squeezing ounces of performance. So we kind of had to go through a soul search of what was important for us. Was it to start being able to build very, very large systems that distribute easily, or was it to build extremely performant systems that are hard to distribute? And so we moved to Scala just for the different layers of processing that we do. Like for example, when a data set comes in, we build a series of matrices as to like how it was constructed, what types of data are within it. Our neural networks then process each individual data point and tell you, like, this is the compound field that I have. And so all of that needs to happen simultaneously, and Scala allows us to solve those problems very efficiently, whereas Rust, we would have kind of had to build out this entire infrastructure. So, yeah.
So I was wondering whether you, in your domain space, if you want to use CPU really hard, maybe use like single instruction, multiple data, single instructions, or MMU instruction set, which many of the JVM doesn't support as well. You probably would need to use something like Rust with a foreign function with C, right?
Yeah.
Did you get into this kind of a situation where you wanted really good performance and?
Not yet. Not yet. And for most practical uses, just the raw Rust implementations worked. There are efficient C bindings, like from Rust to C, and vice versa. So it was kind of a great infrastructure to start thinking about some of the smaller problems that would need to be optimized in the future, but kind of being a scrappy startup, and if the client's code just like runs in 4 milliseconds or a couple nanoseconds, right now it just doesn't matter. As we're thinking about scale, Rust is always in the back of our mind to start eliminating some processing bottlenecks. So, and yeah, so once we start needing those ounces of performance, we'll need them. Yes?
Can you tell more about your experience with distributed systems with Akka? Like how you guys find it useful to you, or how?
Yeah, so definitely the most useful thing for us has been kind of onboarding new people to Scala and being able to package their code within an actor. It kind of allows us to think very sanely in terms of the hierarchical layers of data processing that need to happen for us. And so if you're like a brand new intern and you just need to get up and running, I can give you a very small subset of a problem that honestly, if you start fucking up, I really don't care, because I could just very, very efficiently refactor the little module that we're working on. And so kind of how we early on started architecting some of our code is we have a hierarchy of different actors that take care of work that is kind of broader to more granular. So we have different actors that'll talk to individual endpoints and then relay some information to higher level actors that might be doing an inline join for you, or might be doing some sort of higher level data processing layer, and then eventually like send it back to the client through kind of our highest level actors. So that kind of hierarchical system has worked out really, really well for us, and it's allowed us to onboard many interns who kind of just work on a small subset of problems. So.
And there's another cool part to that as well. So we're using Kubernetes for our infrastructure, and we've had a lot of success with it. One of the challenges, I guess, or one of the things that Kubernetes lacks at the moment is really quality load balancing. So the fact that we are using Akka for the core of our backend systems At a higher level, like the request will come in just round robin from Kubernetes, but then we can use Akka clustering, this sort of much more low-level CPU metrics, and then at the second level down, then we'll actually take advantage of Akka clustering and send messages around to machines that are less resource constrained that Kubernetes isn't really aware of at this point. So that's been a big help for us. Yeah, so we're doing sort of an auto-building Akka cluster in Kubernetes. So we've kind of run it in different implementations, but one kind of cool example is like if you run your Akka application as a daemon set and then set up an auto-scaling group, like as like the overall demands of the system increase, like more nodes will be added, and you now have a new Akka node. We're using Zookeeper, so basically every node that comes online in our Akka cluster reports into Zookeeper, and then everyone else is aware of it, joins the Akka cluster, and then resources coming in are going to very quickly get flowed in at the second level of our actor system, based on sort of the gossip protocol and all the great work that's gone into Akka to make that work. So that's been a big help for us.
Well, thanks, guys. Thank you.